Hey everyone, today we're going to trace the incredible, kind of invisible journey that power takes from the moment it's created all the way to that outlet in your wall.
I mean, you flip a switch and boom, the light's on. It feels like magic, right? Instant. But behind that simple flick of a switch is seriously one of the most complex machines humanity has ever built. So yeah, let's trace that journey.
So this whole trip breaks down into 4 key stages. You've got generation, transmission, distribution, and then finally, you using it, consumption. We're going to start with the power is born, follow it on its cross-country trip, see how it gets to your street, and then right into your house.
All right, first up, generation. Our journey begins at the power plant. This is the starting line for literally every single watt of energy we use.
You know, here's something that's just fascinating about electricity. It's this incredible balancing act. See, unlike water, you can't just store huge amounts of electricity in some giant tank for later. It doesn't work that way. Power companies have to generate the exact amount of power that all of us are using right now, this very second. Think about that. It's a constant, real-time supply and demand game.
So, how do we actually get those electrons moving? Well, for the most part, it comes down to one thing: spinning something. Seriously, whether you're using steam from burning coal or gas, or from a nuclear reaction, or even the force of falling water in a dam, the goal is almost always to spin a giant turbine that's hooked up to a generator. The big exception here is solar, right? Those panels convert sunlight directly into electricity. No spinning required for that one.
Okay, so the power's been generated, but here's the problem. A lot of these power plants are way out in the middle of nowhere, hundreds of miles from where we all live. So how do you get all that energy to the cities without losing a ton of it on the way?
Well, the answer is crazy high voltage. I mean, we're talking up to 500,000 volts. To put that in perspective, that's more than 4,000 times the voltage in a normal wall outlet. It's just an immense amount of electrical pressure.
So why on earth do we need that much voltage? The best way to think about it is like a garden hose. You want to get a certain amount of water from one end to the other, right? You could use a really wide hose with a slow-moving stream, or you could use a narrow nozzle to create a super high-pressure jet. That high-pressure jet, that's our high voltage. It lets us push the same amount of power through the wires with a lot less current, or flow. And less flow means a lot less energy lost as heat from friction. It's all about being super efficient.
And that's why these big transmission lines are basically an interstate highway system for electricity. They're designed to move massive amounts of power over huge distances, hundreds of miles from those remote plants right to the edge of our cities.
All right, so the power has made its cross-country trip on the high-voltage highway. It's now arriving in your neighborhood. But obviously, you can't plug your TV into 500,000 volts. That would not end well. So now it's time to step that power way, way down to a safe, usable level.
And the first stop is this place, the local substation. I'm sure you've driven by one of these and never really thought about what it does. Think of it as the big off-ramp from the electrical highway. Its job is to take that super high voltage from the transmission lines and bring it down to a more manageable level for distributing around town.
Okay, now we're getting super local. The next stop is this guy. That familiar gray cylinder on the utility pole, or maybe it's a green metal box in someone's front yard. This is the pole transformer, and it does the final, critical step down. It takes the neighborhood voltage and converts it to the 120 and 240 volts that your house actually uses.
And that's it, the last leg of the journey. A single wire, called the service drop, runs from that transformer directly to the meter on the side of your house and then into your breaker panel. The journey from power plant to you is complete. Of course, sometimes that journey gets, well, interrupted. We've all been there, right? A big storm rolls in, the wind starts howling, and then bam, everything goes dark. So what's actually happening when the power goes out? Well, almost always, it's about physical damage. I mean, you can imagine, high winds and falling trees are probably the #1 cause of outages, but you've also got lightning strikes that can just destroy transformers, or heavy ice storms that build up on lines and snap them. The grid is pretty resilient, but at the end of the day, it's just out there, totally exposed to whatever Mother Nature throws at it.
So when it's time to get the power back on, there's a very specific logical order to things. The utility companies aren't just driving around randomly. First, they have to repair the backbone of the system, the big generation and transmission lines. Then, they focus on critical places like hospitals and emergency services. After that, their goal is to fix the major distribution lines that will get the most people back online the fastest. And only then, at the very end, do they get to the localized problems, like a single street or just one house. The whole goal is to restore the largest number of customers as quickly and as safely as possible. It's basically triage, and that explains why sometimes your neighbor across the street gets their lights back on hours before you do. You're probably just on a different, smaller circuit that's a little further down that priority list.
So that's the grid as we know it today. But what about the grid of tomorrow? Because this incredible, sprawling system is facing some of its biggest challenges ever.
I mean, think about it. A huge chunk of our grid is just old. Over 70% of our transmission lines are more than 25 years old. They were built for a different world. And now we're piling on massive new demands, like tons of electric vehicles all charging at once. Plus, we're trying to deal with renewables, like rooftop solar, where power flows two ways, both from and to the grid. And all this is happening while we're getting hit with more extreme weather and facing brand new threats, like major cybersecurity attacks. It really is a perfect storm of challenges.
And that really leaves us with the big question, doesn't it? Our world is electrifying faster than ever before. Our demand for clean, reliable power is skyrocketing. So, is our grid actually ready for the future? Making sure this incredible journey of power continues, safely and without interruption, isn't just something we hope for anymore. It's one of the greatest engineering challenges of our time.